Hi, it's Mr. Leong, and in this video, we're going to discuss topic 1.8, graphical representations of summary statistics. The two objectives here are to represent summary statistics for quantitative data using a graph, and to describe summary statistics of quantitative data represented graphically. So if we just think about the types of graphs we already know how to make for quantitative data, the most basic is a dot plot, and then we can make a stem and leaf plot. We can also make a histogram. In this video, I'm going to show you guys how you can make a box plot. So here's the data set that we're going to be working with. It's the weight of Burger King large fries. Right? So every time you go to Burger King and you purchase a large fry, it's not going to weigh the same amount, right? Sometimes they may give you a little bit extra. Sometimes they may skimp out on the number of fries they put in the box. So the weight of the box is going to vary from one visit to the next, or from one purchase to the next purchase. And so we want to kind of investigate this and really kind of think about, well, what is a typical weight for a large fry? What would be considered low? What would be considered high? Is there anything extremely unusual in the weights that we see here? All right, so we have our summary statistics down here on the bottom. And for this video, we're going to focus on the last 5 columns. Okay, that's the minimum, the first quartile, the median, the third quartile, and the maximum. Okay. Those 5 values together are dubbed the 5-number summary. Okay. And remember that the quartiles and the median, what they do is they divide the data into quarters, into 4 equal-sized groups. All right, so for this box plot, we want to first see if there are any outliers, and we're going to use a special way of signifying an outlier. All right, so to do that, we're going to use the IQR rule. So the IQR is the distance between the quartiles. So 163 to 170 is a difference of 7 grams. So I think I forgot to put the units here, but the weights are in grams. All right, so let's check for high outliers. So the cutoff would be the third quartile plus 1.5 IQR. Okay, there's the substitution. The cutoff value is 180.5. We see here that the largest value is 173, and so that's no bigger than our cutoff value. So no high outliers, and it didn't look like that was unusually high anyways. This point does look suspicious, like it could be a little bit too low. So let's see if it falls below the low cutoff value. So now we'll take the first quartile and subtract 1.5 IQR. Okay, those are the substituted values. And here's the cutoff value, 152.5. Okay, so anything lower than this will be a low outlier, and 152 is lower than 152.5, just barely. All right, so we're going to use an asterisk, just a special symbol, to denote that that point there is an outlier. All right, so how can we summarize the rest of the points here? Right, I don't want to kind of focus on individual data, but I want to see the groups, right? What's a low weight, what's a high weight, what's a typical weight? So we're going to take anything between Q1 and Q3 as typical, and we're going to represent that with a box. Okay, so any large fry weighing between 163 and 170 would be considered typical. Okay, the line here in the middle is just to identify where the median is, right? It's 166.5. Okay. All right, so the box represents kind of your typical weights for large fries. And now let's show what would be considered a low weight and a high weight. Well, ignoring the outlier, everything to the left of the box would be considered a low weight large fry. So we'll use a line extending to the lowest point, not an outlier. Okay. And then anything to the right of the box would be considered a high weight fry. So we'll extend a line to the right as well. All right, so what we've done here is we've kind of summarized all the little dots into 4 groups, okay, plus an outlier. So we've got this outlier, unusually low weight box of fries, and then we've got here the lowest group, the group of lowest weight fries. We have 2 groups here in the middle, right, for your typical weight fries, and then this line represents the fourth group, which is the high weight fries. We can actually assign rough percentages to how much data falls in each of these groups, right? We know that the middle group, right, is bordered by the two quartiles, so that's the middle 50% of the data. This line, or sometimes called a whisker here, represents the lowest 25% of the data, and then the other line or whisker on the high side is representing the highest 25% of our data. Right. So to summarize, we could say, you know, typical large fries from Burger King are probably going to weigh in the neighborhood of 163 to 170 grams. Anything from 159 to about 163 would be considered low weight. Anything from 170 to 173 would be considered high weight. And this would be very rare or unusual, right? We wouldn't expect to see anything that weighs this low when we go to Burger King and order large fries. All right, so this is the box plot. It's just a graph that kind of is a quick way to summarize the data. And it basically just shows typicals, lows, and highs. All right, so the next thing I want to do is talk about how the mean and median are related to one another in regards to the shape of the distribution. So let's switch over to my web browser. All right, so what I have here is an inverted dot plot. The dots are just stacking below the number line as opposed to stacking above the number line. And I've created something that's perfectly symmetric, right? So the left and right side are exact mirror images of each other. And you can see here that the mean and median are exactly the same. They're exactly equal to each other. Now, what I want to show you is what happens when we change the shape of this distribution. If we take it from symmetric to, let's make it skewed to the right. Okay, so I'm going to start adding a long tail on the right side. Okay. And so what's happening here, right? Both values are changing, but one is changing more than the other, right? The mean, which is represented by this green triangle, is moving much more rapidly to the right, to the direction of the tail, than the median is. Now, why is that the case? Okay. Well, the longer I make this tail, right, the more extreme values I'm adding to the distribution. And we know that means have to average everything together, including these extreme values in the tail. And since the tail is on the higher side, closer to 10, right, that's going to inflate the average. The median doesn't really care so much about the extremes. It's just focused on which dot is in the exact middle. All right, so pause the video for a moment and predict what do you think is going to happen if I move the tail to the left side, right? If I start dragging these points over here to the left, right, what do you think is going to happen with the mean and median? How will they relate to one another? Okay, so you've probably had some time to think about it now, and it's just a matter of me dragging these dots to the other side. But once again, the mean is moving more rapidly towards the direction of the tail, because now the extreme values are low, right? So having to average those low values in is going to deflate the mean. The median does not average, it's just looking for the dot or the value in the middle. Okay. So the mean is very sensitive to the shape of a distribution. It's gonna pull itself in the direction of the long tail. So if the tail is on the left side, the mean is gonna drift that way as well. If the distribution is right skewed, the mean is gonna pull to the right. It's going to follow the extreme values in the tail.